right. So, welcome everyone to today's class. So I've seen a few of the assignment ones that have come in so far, and things look like they're working out quite well. I know there's been a few issues with the size of the files. So, like I sent out an email last night, if your file is getting huge, let me know and we can figure out a way to reduce it. One thing that we can all do is just get rid of the tree point cloud data right off the bat. So I'm just gonna move this down here. Essentially today we're gonna move into our second topic. So far in this course, we've gone through taking in data from the city of Vancouver, so bringing in our LiDAR data, all our GIS data, and we did this in order to essentially make a site model. So I wanted to share with you guys sort of the proper way of doing that so you can move forward in your own projects, in your own career, knowing full well how to access this kind of rich source of data. That being said, now we are going to move ahead and we're going to start working in the island, the virtual city of Ananav. So essentially the island here. And the reason why we're doing this, like I said, is it's just this sort of self-contained site. And I also do think there's something kind of fun and playful about all working together to build this sort of digital city that we can all sort of zoom around in the end of the course. So all the things you covered in making a site file are not for nothing. Those skills are all very practical. They're the same things I used to build this island, in fact, but now we're going to be switching to the island, like I said, so we'll all share a site file. Now, from this image right here, I did revise Ananav because, you know, the number of people in the class, there was supposed to be a max 60, and now I think we're sort of in the high 40s. So what I did was I revised the site to sort of give us some diversity in lots. So if we open this, so what we're going to do is if you go to, if you go to the Dropbox folder and look in the syllabus assignments folder, you're going to see two files here. So you're going to see the assignment site Rhino 5. You can open this if you have Rhino 5, or the assignment site Rhino 6. If you have Rhino 6, you can open this. Now, in this file, I'm going to be working with this file through this class. This file is going to be sort of the site for the rest of our class. And in particular, each of you is going to choose one lot on this overall site to work through. Now you can see there is already one site right here that kind of has this mass on it. This is my site, so I'm going to be using this one demo site to sort of move through the topics that we'll be covering, and the rest of you will be sort of working on your own site through that. And at the end of the class, we'll compile this model to sort of make our city. So that's how this is going to move forward. So you don't have to choose your site right away. This class, you can just follow along with the site I'm working on. In fact, that might be preferable to sort of make your learning experience smoother. But what I would like you to do is to, in this same syllabus assignments folder, there's also an island lots link. So if you double click that link, what that's going to do is it's going to open up this Google document, which essentially just has a plan. So it's just a Rhino screenshot of the island. I can see a bunch of you are jumping in right now. That's great. And essentially, I want you to put down your name for the lot you want. So, you know, it's kind of first come, first served. I will say that these lots, they're all huge. These lots, because I've reduced the amount of lots, they've sort of gone up to the size to each hold, you know, like the smallest one could comfortably accommodate the Shangri-La. So those are the size of these lots. So I don't think any of these lots are harder or easier than the others. However, that being said, there are some interesting shapes in here, and also if you want to sort of have fun by playing around with your lot's relationship to these freeways, which of course you cannot intersect, cars still need to drive in Ananav. You know, if you want to choose one of these lots, you can have an interesting relationship with that. Another thing I want you to consider when choosing your lot is that for the third part, of course, what we're going to be doing, like I mentioned in the first class, is that we're going to be taking these masses and we're going to be subdividing them into three-dimensional grids. And these grids will develop a system of modules. You know, some will be units, some will be walls, some will be structure, etc., etc. And these modules will be used to fill your mass. Now, these modules will be developed in groups of 4 to 6 because, you know, it will take a little bit of work to develop these modules. So I sort of want to distribute that work across groups. And those groups, there's no kind of clearly defined limits right now, but those groups are going to be based on proximity in the island. Oh, Colin, where is the link to the sign-up sheet? It is in the Dropbox, but I can also just copy it into the chat. So, again, we can, you know, right now I see there's kind of a flurry of activities. So maybe while I'm kind of explaining some other things about the island, you guys can sign up. So I'm not going to assign assignment 2 today. I'll wait till Monday because I know you guys are still kind of trucking away on assignment 1 and I don't want to sort of overlap things. However, when you look at this site file, there are going to be the rules which are going to be used in assignment 2 that will guide our building envelopes. Now, it's worth, while you guys are just looking at it, again, you don't have to choose a site right now. You can wait till whenever you want, I guess by next Monday. But essentially, we're going to be dealing with some things that really you will deal with in your real life career, especially working in a downtown core. And this isn't a Vancouver specific thing. This is going to be a, you know, urban thing in general. So the first thing you're going to deal with when you're working with a site envelope, you're going to be dealing with your max surface coverage, or it can be called max site coverage. What is it's the footprint. So essentially, the first thing we're going to cover in this class is we're going to be dealing with using Galapagos, so this kind of evolutionary solver, to solve a footprint that is 40% of the site. So that's the max site. I have a little image here to sort of demonstrate that. So for example, a site coverage of 25% means that you can cover 25% of the site. Pretty easy. 50% means 50% of the site. 100% will never happen. But that's what 100% of site coverage looks like. FSR, or in this diagram it's called FAR, stands for floor space ratio, or floor area ratio. And essentially what that is you take the area of your site and then you multiply it by a fraction or a full number to get the ultimate area of your building. So in this case, if you have an FSR or FAR of 2, you take the area of your building, of your site, multiply it by 2. Since there's a 25% coverage, you can see that it's stacked, I guess it would be 8 times. If you're covering 100% of the site, you just stack twice. So we won't be dealing with max and min FSR today. We'll be getting into that next week. What we will be dealing with is max height. Now, in the downtown Vancouver core, the max height is actually closer to, for most buildings, around 600 feet. I think the Shangri-La and Trump Tower and all those kind of buildings, they kind of hover around the 600, 650 feet mark. For our island, we're going to be actually working to 820 feet. And the reason why I chose that is because it's 250 meters. And also, when I increase the size of these sites, because there's less people in the class, I found that having a height of, originally I had 550 feet, all the masses just looked kind of stubby. So I wanted to give you guys an opportunity to make some more slender towers. A big thing which we'll be covering today is you cannot shade one north block of your choice between March 20th and September 22nd between noon and 4 p.m. It seems like this weird kind of quasi-magical with a CK weird thing, you know, it seems like it's some sort of pagan ritual, but essentially the reason why cities will dictate shading between March 20th and September 22nd is that these dates are the spring and fall equinox. So essentially the city looks at these two dates and says, between these two dates, it's kind of the sunniest part of the year, the time of the year when people are out, when they're shopping, so therefore we don't want buildings shading shopping districts between, you know, primo outside hours. So in this case, I have noon till 4. In real life, you will not be this lucky. It'll be something like 10 a.m. till 5 p.m., something ridiculous like that. But for Avanav, not only is the city, you know, fully invest in old school freeways, it also doesn't care about shading streets. So it's a little bit regressive in a few ways, but it makes our life easier. And the final thing is your building must stay at least 2 meters away from elevated freeways. So I think that that's going to create an interesting dynamic with some of these sites. And I know that if I were, you know, choosing a site to do a project, I might be very you know, tempted to choose a site like this or like this where, you know, you're ducking in between freeways. I think that could be really interesting. Not that, you know, any of these sites aren't. But that's going to be the basis for building a massing envelope. So you can see what I have right here. This is what we're going to be working towards, is that I've made this envelope. This envelope is based on solar, so that shading calculation, as well as the site coverage calculation, as well as the maximum height calculation. And this might not be the final shape of my building, but given a certain footprint, this is kind of the area which I can build in. So this is what we're going to start working with today. So you can imagine that, you know, you might get something, you could start to develop something that looks like this, that's a little bit more refined within something like this. So that's where we're working towards in the next couple classes, is to start developing an envelope that helps us meet all these stringent bylaw requirements. So does anyone have any questions about that? Okay, excellent. So does anyone have any questions about assignment 1 or anything in general? Okay, so we are going to move forward then. So what I'm going to do is, Megan, are you going to talk about the group projects? Should we? Okay, so 2 questions. First, are you going to talk about the group projects? So the group projects essentially will be developing a module which will fit into your massing. Maybe what I'll do is I haven't essentially laid out assignment 3 sheet. What I'll do is this weekend I'll work on it so we can discuss it well in advance next week. Given that we're all working remotely, I think that, you know, groups should be fairly easy to work in. Collaborate Ultra has a breakout feature that we're going to use, and the group project will not be the entirety of project 3. Essentially what you're going to be doing is you're going to be developing a kit of parts. So for instance, you could develop one of these units together. So, you know, if you have 4 people in a group, you could each develop one unit, and then you each would go off by yourself and take these units that you've devised in a group to put towards your own project. So you're not going to be doing the entirety of project 3 by yourself. I just want to give you guys a chance to work together as a group for a just a class, one class amount of time, maybe a little bit outside of class, just to sort of reduce the amount of work you have to do by yourself. But next week I'll make up a little info sheet to sort of explain that a little bit more clearly. And Zin, should we email assignment 1 to you? No, you shouldn't. What you should do is, if you look in the syllabus assignments folder, in assignment 1, there's a Dropbox link. So if you click on this Dropbox link, it is going to open a page like this where you can just drag and drop your files, and then that will just upload directly to me with a timestamp and all that good stuff. Okay, so let's get massing. So what I'll ask you all to do is, if you want to follow along, just open the assignment site Rhino 5 or assignment site Rhino 6. I also will say, as per the syllabus, maybe we'll do this after the break, but if you are using Rhino 5, you're going to need to install Python for the second half of this lecture. So if you haven't done so, just refer to the syllabus and it'll give you a link for downloading Python. But what I'm going to do is I'm going to work in this demo site. So this island has been made with the same techniques that you guys have been using for your assignment 1. In fact, like I showed you, it's part of West End Vancouver that's been mirrored, then mirrored, then mirrored. Since then, I have gone in and sort of changed the sites to make it a little bit more interesting. And then I've also added this freeway system to kind of add more interest, more variation to the site, to sort of give you something that maybe feels a little bit more real-worldy in a very strange, unreal way. If we look at the layers, I've left a default layer, so that's a layer you can kind of work on. And I've left the untrimmed surface, if you ever need access to that, because all of you, and you know, in making your own site file, you've gotten experience working with these untrimmed surfaces, so you know where that comes from. And of course, I've included the lots and the lot numbers, so these are, you know, the areas where you will work. And I've included on this context layer roads, sidewalks, beach, the freeways, notes, which are these notes here. And essentially, here, I'm just gonna, okay, sorry, I'm just turning off the audio notifications for the chat because Nicholas has it, and I'm sort of, I guess, audio notification sensitive or something. So anyways, we have the context here in the notes. And then I also have this TG massing final product and demo site. What we can do for this is we can just lock all the parent layers because we won't really need them for right now. And you can also at this point maybe just turn off this TG massing final product because we're going to be making our own kind of massing. So we're just working with this. So the first thing we're going to do is we're going to talk about site coverage. So as I mentioned, site coverage is essentially the amount of site you're allowed to cover, the footprint of a building is allowed to cover, and it's going to be the first thing you're probably going to consider when you're working on a tower. You know, a developer will come to you and say, okay, we need an FSR of so much. Also, the city gives us a site coverage of, you know, so much. And usually you want to max out that site coverage because the larger site coverage you have, the more window space you have for stores or public amenities, if, you know, your developer has a heart of gold or whatever. So essentially, it's usually in the best interests of essentially money to have a bigger footprint. So you're going to be dealing with site coverage. what the city will say is you can only have a certain footprint. So in this case, in Ananav, our site coverage max is 40% of the site. So our question then is, okay, given this, lot that we're working with, how can we determine an interesting shape that is 40% of the area of this site? And in the context of this course, how can we do it iteratively and parametrically using Grasshopper? So that's what we're going to do. So that being said, I want you to open Grasshopper. And you will open just a blank document. I'm going to open notes I've prepared just so I don't get off track. And also, while my Grasshopper is for some reason kind of taking its time, to speak to Jeremy, it looks like asked a question about bison. And so, I won't answer that question because it looks like Nicholas answered it. But I do want to mention that, of course, because of the flexibility of the first three classes, we won't actually be using bison today. We'll be using it next week. So this weekend, I'll update the syllabus. Essentially, at the end of section 2, where it says extra topic, if we have time, catch up if necessary. Following that class, everything will be on schedule, but right now we're still in that, area where I wasn't sure how long the site model would take. So I will just open this. Okay, that is all I need. So essentially, when you're working with your site coverage, you're always going to work within plan. Maybe there would be a difference if you were to, work with this 3D surface. Maybe you'd get a little bit extra area because your, site slopes. So you technically have a little bit more area, but when it comes down to it, a municipality is going to look at everything in plan, so you're going to be working in plan. So our first step is going to essentially be to take the edges of this lot and to flatten it out so we can work with it in plan, and that's just going to make our life a lot easier. So what we're going to first do is we're going to reference this surface here. So I'm going to reference my demo site. You can do the same, or you can reference your own site. So to reference this, I'm going to go to Parameters, Geometry, Surface. There we are. And then what I'm going to do is, Bryn, if there is a sign-up sheet for your own site where you need to choose your own site, you don't need to do it now. You can just use the green site if you want to follow along. So I'm going to reference this surface here, so I'll right-click on the surface parameter, go set one surface, and since I already had this selected, I've selected this surface. Now, if I want to, I can always go to my layers. I can turn off the visibility for the demo site layer, and I can see that I've selected the right thing because it's green. I also just noticed that there's some kind of like sketch lines underneath, so you can just delete that if you don't want them. So what we're going to do next is we're going to grab the edges of this site. So to do that, we can simply go to Surface, we can go to Analysis, and then we can go to BREP Edges, and we can take the surface, drag into BREP Edges. So that's Surface, Analysis, BREP Edges. And coming out of BREP Edges, there's going to be three kinds of curves. So since this is just a single trimmed surface, there's only going to be one kind of curve, which is the naked curve, which is all our edge curves. If we select BREP Edges, you can see it's what we want, so that's great. Now what we're going to do is we're going to project it to our construction plane, so our C plane. So that's the XY kind of flat horizontal plane that's underneath this entire model. Its elevation is 0 in the Z direction. And we're going to project our curves onto that to work with this outline in 2D. So to project that, we're going to go to Transform, affine, project. So transform, affine, project. We'll take the output of our naked curves and we'll plug into the geometry input of project. Now you can see what's happening is underneath the island of Ananav, we have this two-dimensional projected line. So what we can do now, since we're just sort of looking at our footprint in isolation, I'd encourage all of you to just sort of turn off the visibility for all the other layers, because right now it's just kind of in the way. So what we can do is we can just go to our assignment sites layer, our context layer. We can maybe leave notes on if we want to remember, 40% coverage, yada yada. But what we have now is just simply our grasshopper, geometry. Now, at this point, what we can do, if we look at the output of our project component by just hovering over the geometry output, we have 8 curves. So a couple linear curves, there are the sides, a couple planar curves, there are the corners. But this is not a closed curve, and to deal with area, we need to close it. To close it, we need to join all these curves into one. So to do that, we can just simply go to Curve, Utilities, Join Curves, and we can put that down on the canvas. We can take our geometry output and plug into the curves input. And now you can see the output is one closed planar curve, so that's great. That's what we want. Now, at this point, we have these 4 components. It seems like kind of a group that does a certain thing. It projects the edges of our site and joins them into a closed curve. So let's group all these together. So I'll right-click outside, click Group. I'll right-click on this group, and then I'll just call it, flattening site edges. So this is the first step. If we want, we can also perhaps preview off everything except for our 2D curves, because we don't really care about the 3D surface at this moment. So we have our curves here, and essentially what we want to do at this point is we want to get some kind of visual feedback of what the area of our site actually is. So it's kind of interesting. The city of Vancouver does keep record of what it thinks the square footage or square meterage of all the sites in the city are. However, from experience looking at a bunch of sites, a lot of the times they're not super accurate. Like their LiDAR data or their GIS data tells them something differently than is written in their written reports. So this is definitely a step that's important to do. You want to actually measure the area of your lot based on the GIS or, probably survey data. So to do that, we have our closed curves. We're just going to go to Surface, Analysis, Area. The curves output is going to go into the geometry input. And now you can see we have 2 things. We have the centroid, which is, roughly the center of the geometry. But then more importantly to us, we have the area, which is in square meters. So what we can do is we can go to Params, Input, Panel. We can, just drop a panel right there. We can take our area output and put it into the panel. And then what we can do to this panel, just to remind ourselves in the future what this actually is, we can right-click on the panel where it says panel on the top. We can say area of site, and then let's put in brackets square meters. So this tells us, like I said, these are big sites. So 23,000 square meters, that's large. If you're like me though, maybe you don't think in square meters as much. So what we can do is we can also have a panel telling us the square feet, because it seems most people think in square feet when it comes to area. Most North Americans, rather, I should say. So what we can do is we can just simply in Google or your web browser of choice, Ask Jeeves. You can go square meters to square feet to get the value that we need to multiply by. And so it's multiplied by 10.7639. I'll copy that into the chat just in case you need it. And what we can do then is simply we can go to math, operators, multiply, so multiplication. We can plug the area into input A of multiplication, and then we're going to multiply it by that 10.7 whatever. So to do that, we'll go to params, primitive, number, I'll right click that number component. I'll change its name to just 10.7639. And then remember, this is just changing the name, not changing the value. So I'll go to set number and change it to the same. So 10.7639, commit changes. I'll put that into B. And then there's the result of our multiplication in feet. So what we can do is we can just take a new panel. So params input panel. We can take the result output, plug it into a panel, right click on the panel and go area of site square feet, like so. So now this gives us 249,000 square feet. So like I said, these are big sites. Essentially, you've all been tasked with making, like massive social housing, buildings. If you're feeling, I guess like a good person, or maybe you're making a huge mall. Maybe it's a hospital. Who knows what it is? It could be all three of those things in one thing. These are large sites. So it could be an amusement park. Who knows? Big sites. So lots to work with. So anyways, this is the area of our site. So what I'm going to do is I'm going to group all these components. I'm going to right click this group, and then I'll just call it area of site. Again, I'd encourage you to save every once in a while. So I just clicked Control S there to save. Now, what we're going to do is if we look at our notes, so our notes layer right here, it says max surface coverage footprint equals 40% of the site. So we've calculated the area of the site, so we can very easily now calculate the max coverage of the site. And what I'm going to do is I am just going to select all of these components we've just made, the entire group. I'll just go Control C, Control V. If your hotkeys aren't working, you could also go Edit, Copy, Edit, Paste. And what we're going to do now is very simply, we are going to, first of all, just right click our group, and we'll call it max site coverage. Just so we remember for future reference, we'll right click this panel, just call it max site coverage. We'll do the same here, max site coverage. And what we're going to do is we are going to right click our area output. So right now this area is just the area of our site right there. We're going to right click on the area output, and just a little refresher, when you right click on an output or input, you have some further transformations you can do to the data. So you can reverse a list, you can flatten it, graft it. We sort of talked about flattening and grafting last time. Simplify, removing extraneous branches. The other thing you can do is you can perform a very simple, usually, expression on the output. So in this case, we have the area, and what we can do is we can say x. So when you're working with the expression editor, it's always x is the variable. So we can go x times 0.4. So essentially what that means is the area of our site times 0.4, which will give us our max coverage of 40%, right? So x times 0.4, and then click commit changes. And now you can see it'll give us the max site coverage of our building. So in this case, it's still huge. Like I said, it's almost 100,000 square feet for our site coverage. And for our in square feet and in square meters, we have a max site coverage of 9,200 square meters. So again, shopping mall size, quite big. So this is going to tell us how big the footprint of our building can be. Now, for your assignment 2 and assignment 3 moving forward, you definitely don't have to max out your site coverage. You just can't go more than the 40%. So you can always touch lightly on the ground if you want to do so. In fact, for sites this large, it might be preferable. So does anyone have any questions about that? So far we've just sort of done an analysis more so than an active procedure on the site. Okay, so if everyone's following along still, what we're going to do now is we're going to start creating a very basic essentially footprint for our building. So the simplest way of doing this, and to be quite honest, probably the most practical way of doing this, is simply to offset the sides of your lot until you reach the max site coverage. So that's what we're going to do first. Oh, Kevin, what was the expression? I'll just copy it there. X times 0.4. Oh, thanks, Brent. So essentially, we're going to offset the sides of this site. So to do that, we have our flattened curves right there. We're going to go to Curve, Utilities, and then we're going to go to Offset Curve. So offset a curve with a specified distance. We're going to plug our Join Curves component, the output of the curves, into the curve input of Offset Curve. And you can see by default it's offsetting by, I believe it's 1 unit. And for me, it's offsetting outward, so it's offsetting in the wrong direction. Yours might not be offsetting in the wrong direction. If it is offsetting outwards like mine, we have to make a little adjustment. If it's offsetting inside on your curve that you're working with, then you can just leave it as is. Since mine is offsetting outside, and of course we want it to offset inside, again, we can use the expression editor. We can right click on our distance input. We can go to expression, and then simply we can write -x. So that means that whatever the input to the distance is, be it 1 or another number we choose with the slider, which we'll do, it'll always multiply it by -1, changing the direction. So you can see I change it to -x, and now it's going inwards. So the next thing we're going to do is, you can see here that, an offset of 1, that probably is not going to get us to 40% of the site. So we're going to get a number slider to help us sort of offset a certain amount. Now, I just like using shortcuts for the number slider, so I'll do this. Probably the easiest way to make a number slider in Grasshopper is to double click on your canvas. And then what you can do is you can just start defining the domain of the number slider. So maybe if it's been a while since you've used a number slider is simply a component that allows you to scroll between the beginning of a domain, so in this case 0, to an end of a domain, in this case 1, and it just allows you to choose a value between those two things. It's like an analog slider on an old piece of audio equipment or something. The way to sort of define those, the end and the start of the domain quickly, is to double click on your canvas, and type the start of your domain. So in this case, we want an offset of at least, let's say, 1 meter. Now, we want to be able to slide in with decimal places. So we want floating point numbers. So what we can do is we can define the amount of floating point numbers we want. So how many decimal places? So I'll say 1.000000. We could do 4 if we want. I'll do 3. And then what you do is type in less than. So that's shift comma, essentially. So less than. And then you can type in your max value. So I'm just going to hazard a guess, and we'll adjust this afterwards. I'll just say, 1 meter to maximum, let's say 100 meters. So 100.000. And then you hit enter. And that creates a number slider that goes between 1 and 100 with 3 floating point values trailing the integer. Now we'll take that number slider and we'll plug it into the distance input. And now you can see that we can offset our curve. Now you can see what's happening here is that we get to a certain point, so around 55, where it offsets too far and we get this error and then weird stuff starts happening. So what we're going to do is we're actually just going to go back in and edit this slider to say have a max offset of 50, because this area looks much smaller than 40% of our overall area, so we can just set 50 to be the max, and then that gives us a little bit of range to test between. So to change the max value, we'll just double click where it says number slider, and then we'll set the max domain, or the end of the domain, to be 50. So 50, hit the check mark, click OK. Depending on your site, yours might be more than 50, it might be less than 50. But this is what you want. You essentially just want to be able to scroll freely between the two ends of your domain, like so. If we want, we can right click on this number slider and just call it like site edge offset. Now, what we're going to do is we're going to essentially use a component called Galapagos. So I believe if you have taken Jason Heinrich's class, he, I believe, used Galapagos, or he might have used Octopus, which is maybe a more complicated version of that. But essentially what Galapagos is it's what's called an evolutionary solver. And the easiest way to kind of explain this is just to go through and use it, especially in kind of a very simple case study like this. So that's what we're going to do. But what's the expression of distance? Just negative x. Yeah, thanks, Nicholas. And essentially what we're going to do is we are going to slide this, or get the computer to slide this slider back and forth super fast, and then we're going to measure the area of the resultant curve, the resultant offset curve, and then we'll compare that area to our max site coverage is defined here. And what the computer is going to do is it's going to say, okay, so I'm going to slide between 1 and 50, and it'll say, okay, we found that we get closer areas if we slide between 1 and 25. So then it'll start sliding between 1 and 25, and it'll say, okay, we start getting closer areas if we're sliding between, let's say, 20 and 25. So then it's sliding between 20 and 25. It gets smaller, and then it says 23 and 25, until finally it lands on some number, like, let's say, for sake of conversation, it's 24.567. And that gives this area the desired area of our max coverage. So that's what an evolutionary solver is going to do. The reasons why it's called evolutionary is that it creates little genes, and it sort of, focuses in on the one that get closer to the area and call ones that don't. But we'll see all of that. But to make that test, to test what offset has a closer area, we need to find out the area of this offset first. So to do so, again, we'll just go to Surface, Analysis, Area. We'll take the curve, we'll plug into geometry. So now you can see we have our area here. It's 13,200. Maybe if we want to see this, we can grab a panel. So you can just double click on your canvas and type panel. So the area I'll put into the panel just to see. And what we're going to do is, this is our current area, and this max site coverage is our target area, right? So we can already see this is too large. So what we're going to do is we're going to subtract this from this. So we'll go to Maths, Operators. We'll go to Subtract. So that's again Maths, Operators, Subtraction. We're going to subtract the area that's coming out of our max site coverage group. We're going to subtract the area that's coming out of our offset curve. So our offset curve area we'll put into B. You can also do it the other way. You can subtract this area from this area. It actually doesn't matter. And you can see what's happening here. Let's say I set my offset to be something, so my area is very small. I'm just going to grab a panel just to show you. You can see what's happening is that the difference between my desired area and my actual area is about 6,500. So what Galapagos is going to do is it's going to reduce the offset until it gets to, something closer. Now, what happens, however, if it reduces it way too far and then all of a sudden we start getting these negative values? Essentially what we need to do is we need to use a component called absolute, and essentially that's going to convert the negative to a positive. So let's go to Maths, Operators, Absolute. So Maths, Operators, Absolute. Take the result of our subtraction, plug into absolute. And now you can see what happens is no matter what, the value is positive. So what the absolute is telling us is it's telling us how far away from a perfect area match we are. So what happens is if we, the offset is very minimal, you can see we're, 13,000 square meters probably too big. If we sort of get closer to where we need to be, that number is going to get lower, lower, lower. So we're getting pretty close to the desired area until we reach a point where, oh no, we're too small. We're now below the desired area, but you can see that the number still stays positive. So it's not showing how much below, it's just showing us how far away we are from the desired area. So this is what you want for Galapagos. Essentially, you want to get it to a point where the fitness, so we'll look into what fitness is, but sort of the target for your solution is 0. So I'll just delete that panel, so I have the absolute coming out. So what we can do is we can group this work we've done here. And I'll right click this group and I will call it offsetting, let's call it lot outline, and comparing area to max site coverage. Does that make sense about the absolute value and the subtraction, what we're doing there? Could someone give me an affirmative, or more importantly, could please someone say, explain it a different way if it didn't make sense? Okay, I'm gonna assume that made sense. Essentially what we're going to do now is we're going to use Galapagos. So what we'll do is we'll go to Params, Utilities, Galapagos. So that's Params, Utilities, Galapagos. And Galapagos needs two things, and it also functions differently than other components maybe you're used to. So the first thing is you don't attach things into Galapagos. Galapagos attaches to other things. So you'll see there's two kind of weird input/outputs in Galapagos. The first one's called genome. The second one's called fitness. So genome is essentially the thing you want to change. So in this case, the slider is making the change. It's affecting the area. So this will be the genome. It's going to be the thing that Galapagos plays with. So click on genome like you would another component and drag it back to the left to attach it to our site edge offset slider. And you'll see it kind of has this lighter than usual wire, but it is there. So just make sure you have a connection like that. The fitness is the define the numbers that represent fitness. So a fitness is essentially the peak value you want to aim for. So in our case, the perfect result is an absolute value of 0, right? Because an absolute value of 0 here means that the area of this offset matches our max site coverage. So what we're going to do is, like we dragged out the genome, we're going to drag out the fitness and plug it into the absolute result. So that's what it should look like. You should have Galapagos attached to the absolute result coming out of the fitness and attached to the site edge offset slider coming out of the genome. Now you can see there's nothing that comes out of Galapagos. That's why it has this little serrated edge there. So what we're going to do to sort of access its power is we're going to double click it. So just double click on the component and you're going to see this screen come up. Now we won't worry about most of these options, but what we do need to change is if we go to options generic, you'll see fitness. We want to click the little subtract sign to change it to minimize. And what that means is since we want our value to equal 0, in other words, the area of our offset to equal our max site coverage, a result of 0 is the lowest possible value we can get. That's why we made it absolute. So minimize, we want the lowest possible value, so we say minimize. Let's say you wanted the greatest difference between this area and your overall area or something, then you choose maximize. But in this case, we'll use minimize. And honestly, I usually use minimize. It seems just to, you usually know what the maximum condition is, so minimize seems to work better. Maybe that sounds counterintuitive, but minimize seems to work for measuring difference. So once you've done that, you can click on solvers. And so you'll see some buttons up here. Essentially, the first button here is use the evolutionary solver, use the simulated annealing solver. We can use just the evolutionary solver. These are both just different algorithms. One is based on, like I said, this, I guess, Darwinian concept of having genomes, testing between them, taking the best result between those genomes and getting rid of the ones that didn't really work out. Annealing, to be honest, I don't really know the the physics that it is based on, but it's based on some metallurgy process. It also works, but I usually just use the evolutionary solver. The other button here is start solver, pretty self-evident. The other thing you can have here is our different previews and also the about. So about is just that nice screen there. But essentially, I like usually displaying all the genome types, and I'll show you what that does. So if we have it on the standard and we click start solver, you might see some changes here, but for something that's simple like this, that's not going to sort of drag down my computer, I like clicking on the display all genomes, because then that means you're going to see this fun kind of wiggling around, and people will walk past your desk at work and go, ooh, what's that? Looks very, very complicated, very scientific. So I clicked start there, and what's happening is this is just a way of showing all the genes. So this is just essentially measuring the difference. And if we look at our slider right here, you can see what's happening is it's sliding back and forth, like I said, right? The computer is testing out all the possible combinations. It's changing the area here. And it's just sort of saying, how can I get closer? How can I get closer? And as you can see, what's happening here is that these are the minimum values it's finding, it's starting to get closer and closer. It'll try different things. After a while, it might get frustrated and try something else. But essentially, it's just trying to solve the closest possible value. If you're not getting anywhere with it, you can always click the additional mutations button. And essentially what that's going to do is it's going to cause it to try more options. So it's going to spread out the ranges that it's looking for. Because sometimes there is more than one position on the slider. If you have multiple sliders, there's more than one solution. So sometimes this button gets it to search for an alternative solution. But usually what's going to happen, especially if you have one slider and a very easily defined criteria like we do right now, is that you're going to see there is going to be a single winner that's closest. So in this case, we have an area that is pretty darn close to our max area. Now, if we, right now we have 3 floating point values, so 3 trailing zeros in our number. Perhaps if we switch this to being 5 floating point values, we would get closer. But ultimately, for all intents and purposes, this is close enough to 0 to count. So if you have a value that's close enough to 0 to count, what you can do is on the right-hand side here, if your solver is still running, you can click Stop Solver. If it has stopped by itself, what you can do is you can just select the closest value, click Reinstate. What that's going to do is it's going to, you can see if I click Reinstate way over here, it's going to move this slider. I click Reinstate, it moves to the closest possible point. I click OK, and now you can see that the area of this shape here is 9,259 square meters. Our max site coverage is 9,258.8. If I were bringing this to the city, I'd just round this number up, round this number down, and we'd say it's the same. If we need to get closer, we can always add more decimal places here. So that, in its most basic way, is how you can use an evolutionary solver to kind of find the perfect site coverage based on your lot. So I've increased to 5 decimal places, so maybe I can get closer. But does anyone have any questions while my evolutionary solver is trying to get closer? Okay. Could someone raise their hand or type something in the chat? I'm just now wondering. Okay, awesome. I just want to make sure that it's still there. Good. Okay, that's great. It's very strange without the feedback, So I'm glad that all makes sense. So that's kind of the very most basic way of figuring out site coverage. Now, a lot of the times, you don't want to have kind of a boring shape like this. Especially for a project like this, I would, very much encourage you to have a base that's maybe a little bit, more interesting. So I want to look at how we can sort of work with different shapes and optimize for different shapes. So I'm going to do this in 2 different ways, and we'll go through both of them. So the first one I'm going to do is I'm just going to switch to the top view, and what I'm going to do is in Rhino, maybe you can make a new layer under demo, maybe you can make your own new layer. I'll make a new sublayer under demo. I'll just go to, I'll call it maybe initial footprint, something like that, who knows. I'll set it to be default. And what I'm going to do is I am going to draw, a shape like so. And maybe I'll actually draw a couple shapes like so. So I'll draw a shape like that, and then I'll draw another shape. Maybe I'll do an overlapping shape actually. So I'll do a shape like this. So, after 5 years of design school, I've determine that this is the peak of design and this footprint is what I want to do. So this is what I'm going to base my area calculation on. Maybe I'll make it a little bit bigger here. Doesn't matter, you can draw whatever. So I'm just going to do that, and essentially what we're going to do now is we're going to look at how we can offset these, merge the areas of these, or maybe separate the areas of these if need be, to create a new area. Maybe I'll make this a little bit smaller, like so. Doesn't really matter. So I just want to show you how you can reference your own shapes. So with this, I'm going to reference both of these. So I'm going to go to params, geometry, curve. Oh, sorry, I have to bring that up. So yeah, I'm going to go to params, geometry, curve. And I'm going to right click this parameter. I'm going to go set multiple curves. I'm going to click 1, 2 curves. Maybe you have 3, maybe you have 4. It'll all work the same. I'll click enter. Now, right now I have overlapping curves. So if I were to calculate area, I wouldn't want to double count this area right there, right? So if you have overlap, it only counts once. So what we're going to do is we're going to offset both of these curves, and we're going to offset them. We'll just offset them by maybe different amounts. So what we can do is we can go to curve, we can go to utilities, offset curve. We can put our curve input into our curve like so. And you can see what's happening here is that my curves are going different ways. So this starts to be a little bit of an issue when it's like one curve's offsetting one way and the other curve's offsetting the other way if you have two different curves. So if this is the case, what you can do, the curve that's flipping outwards, you can just select it in Rhino and you can type flip. And that's going to flip the direction of your curve, but it'll also flip the direction of the curve offset. So if you do have it, you know, like it just was, so offsetting out, offsetting in, just select the curve that's offsetting out and type flip in Rhino, and that will solve your issue like that. So again, we're going to offset by a certain distance. What I'll do is I'm going to grab 2 sliders this time. So maybe let's grab a slider for the first one. So let's type in, let's just say 0.000 less than, and I'll say, you know, the last one had a max offset of 50. I'm going to say 20.000 for my curves. That feels about right. And then I'm going to copy it. So Control C, Control V. So now I have 2 sliders. And I'm going to put them into the distance input right here. So the first one, I'll put it in, and I can see that essentially it's causing some trouble when it gets to around maybe, well, maybe I won't change it yet. I'll put in both first before I decide that. So what I'll do is I'll put in the second number slider, so I'll hold shift. So remember, if you want to put more than one input into a certain node in Grasshopper, you just hold shift till you see this green little arrow and the addition sign, and you drag into the input you want to add 2 inputs into, and then release. So now I have 2 inputs and 1 distance. So this first slider controls the bigger shape in this case. So I can see that I'm starting to get weird, you know, errors around yeah, around 14 meters. So I'll set the max to be 14. Okay, so that looks about right. And then for this smaller curve, I'm getting errors at around 19. So I'll set the max to be 19. And then now I have these 2 shapes. So they offset independently. I'm just going to preview off this stuff here because you can see there's that extra line there. So now we have these curves like this. We're going to do something very similar. We're just going to measure the area of both of these, but what we do need to do is we have to measure this intersection here. We don't want to double count it. So to make sure that we don't have this double counted, what we're going to do is we're going to go into intersect, and then we will go into shape, and then we will go into region union. So intersect, shape, region union. The curve, so the offset curves, I'm going to put into region union. And if we look at the result, there's two curves coming out. So in the chat, or if someone wants to shout it out of reverse, flatten, graft, or simplify, which of these should I do to combine both of these curves into one list? Flatten. Awesome. So we're going to choose flatten. That combines both of these into one list, and now you can see that this component works. So now if we offset this one more so that they don't overlap, that's fine. We get two curves, but what we want to make sure is that we don't double count this area here. Now, one thing I do want to mention is we're going to take a little extra step here and make a surface. So we're going to go to Surface, Freeform, Boundary Surfaces. So we're going to take the result and put it into the boundary surfaces. So again, that's Surface, Freeform, Boundary Surfaces. And the reason why I'm doing that is I don't have a situation in this shape where I may have a, what you call it, a compound curve. So I don't have anything that's like this, you know, another curve in here. But if I were to have, you know, something like this, oh, this is going to mess everything up. If I was going to have something like this, it should, oh no, I made it too wild. You wouldn't have an empty space like that. But if you were to have something that kind of doubles in on itself to create a little opening, the boundary surfaces will, or at least in theory, kind of solve that. So right now it's not doing much, but for you know, your situation, throwing in a boundary surfaces at the very least is going to help you catch some glitches that might come up. So that's why I add that in. So I'm just going to go back and add those in the right order. Okay, so I have these offsets now. I have these surfaces. Now what we can do is we can just go to Surface, Analysis, and then Area. And we're going to take our boundary surfaces and plug into the geometry input. And I want to address Natalie's question. So yeah, so what Nicholas said is like right how you set the max, but yeah, Natalie, to answer your second question, is just manually making sure it doesn't go past the border. There could be some kind of advanced cases where you're not sure it will go past the border, and in that place you have to use some sort of more advanced Boolean logic to, you know, essentially have a limit switch to make sure that it doesn't mess up. In our next example, we'll actually kind of have a little bit more advanced Boolean logic to kind of make sure you don't go past a certain limit, as it were. But for this, yeah, it's just easiest to, you know, check it by, you know, by eye. So we have our areas coming out of this. Now, since we're in a situation where right now we have one area, but let's say we offset this and now we have two areas, what we need to do is we need to add up these areas just in case. So if we only have one area, it doesn't really matter. If we have two areas, then it'll be good to add it up. So what we're going to do is we're going to go to Maths, operators, and then mass addition. So all this does is it adds up all the values that are fed into it, and we're just going to feed in the areas into our mass addition. At this point, I've sort of maybe gone a little bit too far without grouping, so maybe what I'm going to do is I'm going to group my sliders to my boundary surface, because this is kind of the section of the definition that creates the surfaces after offsetting the curves. So I'll just select these, I'll group them, I'll call this group offsetting curves and creating surfaces. And now the area in the mass addition, I'll just group these together and go measuring area. So we have a result here. Now, what we can do now is we can just simply compare it using Galapagos again. So it's going to be pretty much the same thing here. So what we can do is we can go to maths, operators, and then go to subtraction. So maths, operators, subtraction. Again, it doesn't matter what is subtracting what, because we're going to throw an absolute after this. So I'll take our mass addition result, put into A, and I'll take go way back up to my max site coverage group, take the area from my max site coverage group, plug into B. So what this subtraction is now measuring is just the distance between these two areas. And then after that, because I want to avoid having negative results, so let's say the areas of these two shapes is smaller than the max area, I still want it to be positive, so Galapagos works. So what I'll do is I'll go to maths, operators, absolute. I'll take my subtraction result, plug it into absolute, and that'll give me the difference between the max allowable area and our current area. Once we have that done, we can go back into Galapagos. So what we can do is we can go to params, utilities, Galapagos, and we'll click on Galapagos. The genome, so drag out from Galapagos, the genome will go to first our slider number 1. And then what we can do is we can hold shift and drag out a genome again. So holding shift, our little DNA strand turns green, we get a little plus icon. Drag that out to the second slider. So now you can see if we zoom in or if we click Galapagos, the genome is affixed to both of these sliders. And now what we can do is we can take the fitness and plug into our absolute. So then your definition, at least this section of it, should look something like this. And now it's the same as we had before. So we can double click on Galapagos, set our fitness to be minimized, because we want the minimum difference between our max site coverage and the site coverage of our shapes. Go to solvers, choose evolutionary solver. Maybe I'll choose annealing solver just to see it. So I'll say annealing solver. I'll select the display all genomes because I like seeing this geometry dance around the screen. And I'll click start solver. Okay, so I'm going to stop the solver here. Maybe I'll press the skip to the next annealing track. sort of see multiple variations is. So I'm going to stop the solver. Okay, so this is interesting because what's happened is, in this case, we can essentially look at all the variations here, right? So if we go to reinstate, we see the closest one. We can go back. Now, I don't use the annealing solver as much, so honestly, I'm not sure how we take the values from our other annealing track, as it were. But anyways, this is one potential value, essentially, right here. But what we can do, let's go back to the evolutionary solver. I'm going to go start solver, see what we get. This is kind of the one I like. And you can see what's happening here is it's giving us one solution, right? So our big shapes offset about 2, or small shapes offset about 13, but we can also click the additional mutations button to sort of shake this up more. So the more I click this, you can see the more variation we're getting. So what do the dots in the bottom left indicate? So these indicate, I believe it represents in a very abstract way, essentially, this would be like a grid on which the values in the slider are moving, and this is, I don't know, showing you the solutions in a nutshell. Not sure. If you want more information, you can click on these evolutionary principles applied to problem solving, evolutionary solvers, fitness functions, etc., on this opening page, and I'm sure it tells you. So if we look at this, we go to reinstate. Essentially, you can see that we're getting kind of the same solutions here, right? So sometimes what I like to do is essentially what we can do is we can reinstate this. And I mean, there's tons of ways you can do this. You could simply just screenshot these solutions. You could write them down. So, Ellen, is the speed is going through the options just the computer's capability? Yes. But I will go over a way to sort of reduce the runtime. So you could always just copy these values and you could just save them to a spreadsheet, essentially. So you could always say this is one solution, right? So maybe we can essentially just copy data only. Let's just double click here, Control V. I'll right click this panel, go copy data only, just grab another panel, Control V. So these are two solutions. Now, I have two sliders, and maybe this one, you know, it's offsetting this slider by about 13. Maybe I want something where this one is offset a little bit less. So what I can do now is I can just go back to this slider and limit it. So maybe I say, I don't want this one to be offset so much. So maybe what I do is I just double click on this number slider. I change its maximum value to, let's say, 4. Click OK. So now this one has less room to wiggle around, which means this one's going to have to move more to reach that our target. So what we can do is we can double click on the evolutionary solver again, Galapagos, make sure it's set to minimize, solvers. To address Ellen's question, essentially what we can do is we can say only display better genomes in the Rhino viewport, or else do not display any genomes in the Rhino viewport. And if you're not displaying any genomes, or you're only displaying the bare ones, what's going to happen is you're not going to see the same amount of shaking. It's only going to show you sort of the best new solutions it comes up with, and then that will speed up the performance. You know, I will say though that there are times where you use, you know, Galapagos and you just let it run for like a day. So for very complicated issues, it will take a while to go through all of them. Thank you, Nicholas. So that looks like an interesting read if you want to sort of look behind the dots. So we can go to reinstate, and now you can see that we have a much different kind of outcome than our original outcome. So our original outcome was, 2.025. This one is 6.6 offset on the larger shape, and then 1.7 offset on the smaller shape versus 13. So that's a way to sort of create some variation in your shapes, as it were. So does anyone have any questions about sort of offsetting more than one shape? Okay, so I'm going to show you how to do one more thing, and then we'll take a break. So sometimes what you want to do is, rather than offsetting all the shapes by a certain amount, you're going to want to maybe just offset one side. So what I'm going to do is I'm going to disable all of this stuff here. I will just delete these curves, and I'm going to start anew. So what I'm going to say for this design problem, what I'm going to do is I'm going to draw, let's say, like a building that goes like this. So this is the building that you and your team have determined. Like so. Now, currently, it's larger than 40% of the site. But your question is, how could we draw a line, so let's say a line like this, that moves like this, and how could we move this line back and forth in this direction that essentially creates the required area on, let's say, this side right here, so we need to define the side we want to keep, that matches the area. So that's the issue. So essentially we're going to say the intersection between this line, this shape here, we want the area. It could also be a line, maybe let's make it a little bit more interesting. We could say we want to move this shape like that and find the proper area. So if that's your problem, essentially we will solve it. So let's reference these two curves. This bigger curve, so just draw a bigger curve that's probably too big. And we will call this, so we'll go into Grasshopper, we'll go params, geometry, curve. I'll right click this curve, I'll go set one curve. So it's selected because it's green. This curve we'll call it the slicing curve maybe. So let's go to params, geometry, curve. I'm going to right click this, go set one curve. So I'll right click this, call it the slicing curve because it's slicing the main kind of footprint. And essentially what we're going to do is we're just going to sort of define a vector to move this curve. So to do that, there's lots of ways you can define a vector. Maybe the easiest way to do it right now is to just draw it in Rhino. Sometimes it's easiest to, rather than, in my notes, I have like a slider where you can change the angle. I think honestly, probably the easiest way to do this is just to draw it in Rhino. So essentially what we're saying here is we have this cutting curve, and we want to move it along this curve that we drew like this, right? Now, we could always, in Rhino, easily change the direction of this curve. So it's not like it's not flexible, it's just we're doing some of the legwork in Rhino. So this third curve, draw that's the direction that this will move along. We'll go to params, geometry, curve, set one curve, and we will call this movement curve. Now, to move this slicer curve along the movement curve, we'll position this curve, since the end of this curve is on our slicer curve. So essentially what I did was I just drew our movement curve from a point on our slicer curve to the end of this area. What we can do very easily is we can just go to curve, analysis, and then endpoints. And the endpoints, I will attach the movement curve output. We'll go into the curve input in the endpoints, and you can see I have my start curve and my start point and my endpoint. What I'm going to do now is I want to define a position on this movement curve that our slicer curve moves along. So what I'll do is I'll go to curve, analysis, and then I'm going to go to evaluate curve. And what I'm going to do is I'm going to plug my movement curve into the curve input of evaluate curve. And then the parameter, we're going to set a number between 0 and 1. So if we remember, you know, from previous classes, if you've had me as an instructor, or maybe someone else told you about it, every curve has essentially a parameter, right? So a curve that's wavy like this can still have a parameter between 0 and 1. So we can say 0 to 1, 0.5 is the midpoint, right? Now, sometimes when you draw a curve in Rhino, like I did right there, your curve might start from a value of, let's say, you know, 200, and it might go to 3033. Yeah. 200 and 3033 are arbitrary numbers I've chosen. The values that Rhino chooses is usually based on their XYZ coordinates, but for our intents and purposes, they might as well be totally arbitrary. What you want to do is you want to reparameterize, and that will set your curve's inner coordinate system along the curve to be 0 to 1. So when I say the parameter on the curve, that's what I'm getting at, this parameter between 0 and 1 along the curve. So what we're going to do to make sure that this curve is indeed reparameterized, has a parameter between 0 and 1, we will just right-click on the curve input in our evaluate curve, and we'll click on reparameterize. So that will set its parameter from 0 to 1. So now when we go to params input number slider, and plug this number slider that goes between 0 and 1 into the parameter, you can see that now we have a point which moves across the entire length of our movement curve. Now simply what we're going to do is we are going to create a 2-point vector between the start of our curve. So right there, we've graphed the start of our curve and the point that we are choosing moving along our curve. So we'll go to vector 2-point. Point A will be the start. Point B will be the point on the curve. And now what we'll do, we have this movement vector. It's invisible, but it's there. We can go to transform, Euclidean, move. And our slicing curve, so this curve that we've referenced there, yours might be a different shape, we can put into geometry. In the motion will be this vector 2-point. So now you see we have this kind of curve moving like that. Now, like, you know, our offset, a lot of the times you might want to limit your range. So you might say, okay, if we're dealing with this area here, maybe this is too small, or maybe we don't want a situation like that, which will cause an error. So what I'd do is I'd just find a point that, you know, is the limit of sense, essentially, and sort of restrict your number slider to that limit. So in my case, it's 0.745. So what I'll do is I'll just double click on this number slider and set my max value to be 0.74. Click OK. And now you can see my shape moves between those two extremes in my shape. We have our curve here, which is our kind of big footprint. Simply what we can do is we can go to Surface, Freeform, Boundary Surfaces. We can plug our footprint curve into our Boundary Surfaces component. And then what we're going to do is we are going to go to Intersect. We're going to go to Physical, and we're going to go to Surface Split. So Intersect, Physical, Surface Split. The surface will be our boundary surface, so our big footprint. Plug that into Surface. The splitting curves will be our moved cut curve. So you can see as we move this along, what it's doing is it's splitting up our big footprint like so. And you can see that usually at the outset there's two trim surfaces. Maybe at the very beginning there might be 3 trimmed surfaces. Oh no, there's only 2. So this is still, yeah, so this is still considered as one surface. So there was a question earlier about, so Natalie asked about, you know, setting the limit manually, and, you know, Nicholas and I were both sort of answering to the effect of, it's easier to do this, right? Sometimes it's easier to just kind of set by eye rather than figure it out. What we have now, though, is a problem that we can't really do that same kind of human intuitive logic to, unfortunately. And what that issue is we are splitting this surface, right? And we want to calculate the area of one of these fragments, but essentially the computer maybe doesn't know what fragment we want. What makes it worse is sometimes, and not always, you'll find that if you choose, let's say, the second surface in this list that comes out of this surface split, sometimes it flips. So let's see if it does it here. I don't think it will, but let's see. Let's go to Sets, List, List Item, just to see. So let's see. Will it flip? It doesn't flip here, but you know, sometimes you will find that it'll just kind of flicker, right? So it'll choose this surface, it'll choose this surface, and you don't want that to happen. Maybe let's see if I can make this flicker. Yeah, so if I make it split like this, you can see now it's like, okay, it's choosing this one surface there, but then it's choosing this surface. Maybe we want this surface. You know, we don't have a lot of control over it, right? So essentially, we need to figure out another way to choose what surface we want, as it were, to measure the area of. So, I mean, I have a particular way that I could think about doing it. Does anyone else have a way that they might think about solving this problem? So always choosing this surface? What kind of logic do you think we could feed the computer to always choose this surface? So, you know, maybe you thought about something. I know this format, maybe it takes too long to type. There's a bunch of ways of doing it, but I'm going to choose one way. Essentially, what I'm going to do is I'm going to take the center point of each of these surfaces, so the centroid, and just see which one is closest to this endpoint, because we already have it, right? And if we want to choose the surface that's on this side, we could just choose the one that's closest to this start point. So that's one way that works in this situation. So that's the kind of logic you need to incorporate. So let's simply just go to Surface, Analysis, Area. So there's the centroids. And now what we're going to do is we're going to measure the distance from this endpoint, and whichever one's closer is the side we want. So we're going to go to Vector, Point, Distance. the distance between the two centroids will be the two centroids will go into point A. Point B will be the end point of our line. So end point there. And that's going to give us the distance. So you'll see that we get two distance coming out. So one is 126, one's 37. So the distance between this point is 126. The distance between this point and the end point is 37. So what we can do now is we can sort these distances. So let's go to sets, list, sort list. The list we want to sort, the keys, is going to be the distances. So what this does is, we put in 126 followed by 37. It's just going to sort it numerically. So it goes 37 to 126, right? It's kind of like counting. But what we can do is we can synchronously sort a second list of values. So in this case, what we can sort is the fragments themselves. So it'll just perform the same transformation on the list. In this case, it will take the first item in the list and put it to the end of the list. It'll do the same thing here with the fragments. It'll take the first item of the list, which is this surface here, and put it to the end of the list. So let's put that into values A. We're going to need one more thing coming out of this. We'll also need the area, because we're going to use that for the Galapagos analysis. So what we can do in sort list is we can zoom in. We can press the little addition button. So we have another input A. We can take the area that's coming out of our area component that's giving us the centroids, plug those areas into A. So now we have the sorted surfaces, or we have the sorted distances coming out of keys, the sorted surfaces coming out of values A, and the sorted areas coming out of A. Now what we need to do is just choose the first one out of these two lists because they're closer. So let's go to sets, list, list item. So the list to analyze is going to be values A. The index, item index equals 0. So that's the first item in the list. By default it's 0. So we want the first item in the list. So we'll just use it as default. We also want the area of this shape. So we can go to sets, list, list item. So A goes into the list. You can see it gives us the area. So 6,832 square meters. And what we can do now is let's just preview off all this stuff. I've gone a little bit sloppy in my grouping. Don't get sloppy in your grouping, please, in your assignment, but just for the sake of time, I've gone a bit sloppy in the grouping of this definition. But essentially right now what we have is a surface to measure the area of and the area itself. So we can just do the same thing here. So I'll just very quickly go over this in about a minute, just so we can take a break and then jump back into the next topic I want to cover. But we have our surface here, and we have our area here. So what we'll do is we'll go to maths, operators, we'll go to subtraction, we'll take our area. From our area, we will subtract, we'll go way up to the top, the max site coverage, so the area coming out of max site coverage, we'll plug into B. We'll use the component abs, so absolute. So if that's our maths, operators, absolute. And now we can use Galapagos on this. So we can go to params, utilities, Galapagos. The fitness is going to be the absolute. So we can take our fitness output, plug it into absolute. The genome will be our slider at the beginning. So plug it there. So you can see Galapagos is connected to our slider. The absolute is our genome. And now what we can do is we can double click Galapagos, set our fitness to minimize because we want to reach a value of 0. go to solvers, choose evolutionary, annealing if you want. Set your display value to vary the speed that it solves, and then click start. So in a case like this, if it's running for a while, you can see this 1.36 looks like it's going to be about the closest it's going to get. We can just go reinstate. Now, if this is close enough for you, that's great. If you want to get it exact, what you can also always do is we know that we're around 0.242. We can always double click on our slider. We can change its domain to get a little bit closer. So let's say between 0.2 and let's say 0.3. And then we can crank the digits to be like 6 digits. And then we can go back to Galapagos, set to minimize, solvers, start solving. And then you'll see what it'll do is it'll just be able to iterate through a finer grain of values to get even closer. So you can see now we're off by 0.06 square meters. So we're now in the range of being off by like a few square centimeters. So we're really quite close. So does anyone have any questions? What we're going to do now is we're going to take a break till maybe I'm going to say 7. I'll start again at 7:47. Just grab some more water, and then we're going to jump into another topic, but I'll sort of monitor the chat as well, so I'll answer some questions before. Let's just say 7:50. So we'll be back at 7:50, but I'll monitor the chat until then. Resume the recording. Okay, so yes, Meredith, it will. Will reinstate the value that shows up, last. So essentially, this will reinstate the value that gives you that divergence, or that divergence there. So yeah, it should move the slider. Now, it might be that the values are so close, or the values are the same. If the values, for example, these values are the same, so they're not going to move the slider. So it should move the slider if the values are different, but it won't move them if they're the same, necessarily. Further than that, if you still get that error, we can sort of look at it after the class. Okay, so while my computer is kind of freaking out at me for trying to stop the solver, apparently. Oh, good. There we are. So I did want to point out, just right now, actually, I've updated the syllabus to include Nicholas's contact info. So, feel free to reach out to me if you have any issues. But of course, Nicholas is happy to take your questions as well. And I mean, you can always email both of us at once. That might actually be the best way to do it. Just email us both in the same email, and then whoever gets to it first, you'll sort of be assured the quickest possible answer. In Nicholas, it's not a race. So that's probably a good way to go about it. So what we are going to do now is these massing based on curb shading. So, and also based on the maximum height. So in the city of Vancouver, like I said, they essentially want to prevent tall buildings from, shading things like parks or shading, popular retail streets. And as a result, and you'll see this a lot in towers, you'll sort of see setbacks that happen at an angle like this. Classically, what you would see is angles that sort of step back, like in this Hugh Ferris illustration. If you think of, like, for example, the Chrysler Tower, They step back, and that's to prevent excess shadowing. So that's what we're going to do now. We're going to use a curb as sort of a datum from which we are casting a shadow. And then we're going to derive a shadowing envelope. So essentially, we're going to come up with a shadow envelope that, ensures that we don't shade a particular curve. So what we're going to do is we're going to start from, some sort of site footprint. So in this case, I have this surface that I ended up with here from my last analysis, so maybe I'll work with this one. You do not have to work with this. You can just draw, a rectangle in Rhino. It doesn't really matter. Essentially, all you want to do right now is just have something that's a stand-in for your footprint, right? So you've solved for your footprint. So what I'm going to do is I'm going to right-click on my final surface I have right here, or maybe let's just make it a curve. Let's do a curve. So if you have a surface, we're just going to go surface, analysis, brep edges to get these naked edges. We're going to go to curve, utilities, join curves. And essentially what I just want is some joined curve like this, right? So I'm just going to bake this. I'm going to, just close the Grasshopper file, show you what you want. So essentially what you're going to want is essentially a curve like this. So this is, I'm saying, the footprint of my building. So if I turn back on all the different layers, so we can turn on the demo site, you can see I have this flat shape that's underneath my site. We can turn back on the context. We can turn back on the assignment sites. So you can see that essentially I just have my 2D curve underneath my site. So what we're going to do is we're going to take this curve, we're going to move it up to my site, and then from there we're going to essentially create what are called solar envelopes, and then we're going to use them to create a massing envelope. Okay. So let's open Grasshopper again, but just make sure you have on all the visibility like this. So when we're creating a solar envelope, essentially what we need to do in real life, what you're going to get is you're going to get a situation where a building is not allowed to shade a certain park or a certain street, as I mentioned. So for example, if I open that that image I had here, what happened in this situation was that, we were working on a building and it was not allowed to shade a park that was to the southeast of it. So this corner here, so you can see I have this big kind of plane here that prevents it from shading. And it also wasn't allowed to shade the sidewalk across the street. So that's caused this other cutaway from the mass. So this is the basic premise that we're going to work from. So now the thing about our site and the fact that all of these sites are varied is that there's a whole bunch of different sidewalks that you could, avoid shading, right? So as a result, for your assignment 2, which I'll give you, the assignment sheet for on Monday, you cannot shade one north block of your choice between these times. So what I mean by one north block of your choice is it's kind of an easy thing, and I want you to choose whatever gives you the most interesting shape. So I don't want you to be choosing something that gives you, the most restrictive form, unless you want to do that. What I'd encourage you to do is sort of analyze a few different curves and choose which one you think will give you the most exciting thing. So for example, I could set out a little bylaw for myself saying that my site cannot shade this curve right here. Or maybe I say my site cannot shade this curve right here. My site cannot shade this curve right there. As long as the curve is to the north of your site, you can choose it. So I could choose this one down here if I really want to. The only thing is it needs to affect your site. So this one here might not actually affect my site. So you'll see what I mean in a bit. For assignment 2, I'll just point out right now, if you've chosen a site, for example, I guess 22 or 29, you can't shade the water. Let's just say that. You can't shade the water, so this beach is your edge. And if you are kind of on the edge here, so 1, 4, 6, 10, 14, 17, or 37, 40, 42, 46, 47, you can choose, for example, a lot to your northeast or northwest as your curb, but you can also choose the shoreline if you want as well. So essentially for all of this, you can choose whatever curb or shoreline you want. It doesn't really matter. The thing that matters is you know the technique of how to do this. Now, all that being said, to figure out how not to shade something, essentially you need to know the angle at which the sun is at. So I'm just going to look at our lecture files. If you go into the lecture files for today, which has the wrong date, it should be 06/24. I'll change it after this. I just don't want to mess up syncing right now. In lecture images, essentially there's altitude and azimuth. So essentially we want to know where the sun is in comparison to our site. So the azimuth is the angle measured from north, and the altitude is the angle matched from essentially the horizontal horizon. And this gives us the solar position. So when I talk about altitude and azimuth, that's what we're talking about right now. So we need to know the position for this for Avnana, that's how you pronounce it right now, at any given time. For the sake of our exercise, we're going to say it has the same coordinates as Vancouver. So also in today's class, you'll also notice there's a solar vector calculator. Now, this is a component that I made myself that you're all welcome to use and, into perpetuity, and it's super helpful. So what I want you to do is to open Grasshopper, and we want to essentially open that component. So in Grasshopper, go File, Open Document, and then just navigate to today's class folder and open that folder. Like I said, if you're using Rhino 5, you needed to install Python. So Solar Vector Calculator, and it's going to open up something like this. Now, what this does, like I said, is a custom, set of components. Is very basically, it just tells you the altitude and azimuth of the sun based on a latitude and longitude. So essentially, you can see that there's two components. One is the date, so we'll look at that. And then it gives you an output. It tells you the days being analyzed, the sample times, and then it'll give you this other kind of Python gobbledygook that goes into another component that gives you the solar vector. So it gives you the altitude and azimuth is a Rhino vector. Now, it needs a couple inputs. So it also needs the longitude and latitude and the time zone. But essentially, you can find this stuff online. So for longitude and latitude, to find the longitude and latitude of a place, essentially it's just the position of a place in the world. You can just simply look up, Vancouver, longitude and latitude. And essentially it's going to tell you the longitude and latitude. Now, you'll see here that essentially it's 49.2827, 49.284597, etc., etc. Essentially, and then 123.12. You'll notice that here it says -123. Essentially, that's because these are GPS coordinates, so they have an absolute value for longitude. So the second value. In our case, we have a negative value. So you can just go to latlong.net it's one that pops up, and this looks closer to the latitude and longitude that I chose. So that's sort of just how you choose it. So if you want to analyze a different city, feel free to enter in a different latitude or longitude. This other thing we need is the time zone. Now, time zone is the UTC, and essentially you can look that up. And the only thing you need to be conscious of is daylight savings. So what you can do is you can look up Vancouver daylight savings, or another place daylight savings, and it's going to give you essentially so time difference to GMT / the universal time is going to be, so if it's not daylight savings, so standard time zone, it's going to be -8. Current time zone offset, because we're in daylight savings, is -7. So that's where this -7 comes from. The reason why we choose daylight savings time is because most of the solar analysis you're going to do are going to be in between March 20th, which is the spring equinox, and September 22nd, which is the fall equinox. And essentially what's going to happen is, it's daylight savings time between those two dates. You can double check when daylight savings time is by just looking up daylight savings. So in the Vancouver context, if you're between March 8th, November 21st, if you're using this tool, you need to set your daylight savings to -7. If you're doing it for another location in the Earth, essentially you just need to change the latitude, longitude, and the time zone. Now, for future reference, if you're wondering where all this came from, very simply, I went to the NOAA, so that's the National Oceanographic and Atmospheric Agency, so it's a US government agency, and essentially they give this solar calculator, so they can, they give you the altitude and the azimuth for any place in the world, but kind of very kindly of them, they also give you the solar calculation details. They give you an Excel spreadsheet if you want, so this is kind of interesting if you want to look at it. Originally, I thought in class we might actually play around with this Excel file, so you can change your latitude, longitude here, change your time zone here, and it's going to give you all these interesting sunrise, sunset, etc., etc. But instead I thought, okay, I'll just use the tool I have at hand. So what I did essentially was I went through this spreadsheet and just converted all these calculations to Python. So that's how it works. These calculations are based on astronomical algorithms by Jean Moose, which I think was written in like the 70s. So, pretty accurate guy, still using them. I find it funny here in this website, data for litigation, apparently do not use the component I made in a court of law. It might vary significantly from actual observed values. That being said, I've measured this in real life. It's pretty spot on, and it's going to be much more spot on than, let's say, SketchUp or Rhino or Revit. So, like I said, these components here, feel free to use in the future. They're quite useful. So what's going to happen here is essentially we are going to calculate the altitude and azimuth of the sun based on some input dates that we say here. Now, you need to be careful with this component because it will calculate all of the angles in a range. So for example, right now, I'm saying give me all the solar angles between March 19th, 2020 and April 1st, 2020 between 10 a.m. and 4 p.m. So you need to use this format, the 24-hour format, and for every 10 minutes. So you can see that the analysis days are March 19th, March 20th, March 21st, all the way up to April 1st. The sample times are 10, 10:10, 10:20, 10:30, 10:40, all the way up to 4 p.m. And we're analyzing it for Vancouver. And if you look at the amount of vectors that come out, we are analyzing it for 518 moments. So You can imagine that if we were going to analyze for, cannot shade between March 20th and September 22nd, all of a sudden the amount of vectors we're calculating, increases a lot. So what we're going to do instead, and the reason why the city chooses the spring equinox and the fall equinox, is they're kind of worst case examples. So what we can do is we can calculate the vectors for March 20th, we can calculate the vectors for September 22nd, and if we're fine for those 2 days, then we're sure we're going to be fine in between those 2 days. So let's calculate the solar vectors for March 20th between noon and 4 p.m. How would we go about doing that? Simply, you can slide your clock at the top here, so the start date to 2020, March 20th. You can go down to your end date here, slide the top calendar to 2020, March, set it to 20th. So now you can see the analysis days is just 2020, March 20th. So we just have one analysis day. The start time, 10 till 4. If we look at our analysis period, Avnana has a less strict set of guidelines, so we are just analyzing between noon and 4. So let's set our start time to be noon. It's a 24-hour clock, so we'll just write 12, colon 00, noon. Click OK. 16 equals 4 o'clock. That's 4 p.m. on a 24-hour clock, so we're fine, 12 till 4. In every nth minute, right now it's calculating every 10 minutes. I mean, we can do that, and you can do that, but honestly, I'm just going to say we'll calculate every 30 minutes. So we'll calculate the solar vector every half an hour. So now you can see we're getting the solar vectors for noon, 12:30, 1 p.m., 1:30, 2, 2:30, 3, 3:30, and 4. And since our latitude and longitude are Vancouver, please, for the sake of this course, keep these latitudes and longitudes and time zone the same, just because we want everyone to work to the same standards. They're going to give you some output vectors. So these are some solar angles. So essentially, vectors, of course, like we know in Grasshopper, they're just a direction. They don't do much. Essentially, what we want to do is we want to convert these into shadows. So maybe first let's just see the direction of the vectors to kind of see where they are. It might be interesting. What we can do maybe is I'll go into Rhino. I'll just click on the single point. I'll just place a single point. So I have a single point there. So again, click point. Just place it wherever. I'm going to lift it into the sky because it's going to represent the sun. So there's my little pointy sun. And I'm going to go to display, vector, vector display. My anchor is going to be the sun. So I'm just going to right click anchor, go set one point. Point object to reference, type will be point. I'll select my point there. And then the vector will be the vectors out of here. So my solar vectors. So if we zoom into this point, you can see that we have a whole bunch of different vectors coming in. So these are the rays of the sun. So they're sort of casting down that way. If we want to, we can change the amplitude of these vectors. So let's go to vector, vector, amplitude. Take our solar vectors, plug them into the vector input of amplitude. And let's change our amplitude to a random value. Well, not random, a long value. I'll right click amplitude. I'll go set number, and I'll set the number to be, let's say 100. Go commit changes. And now let's take the vector that's coming out amplitude and put into the vector. And now we can see a little bit better the solar angles between noon and 4 coming from the sun. So these are the sun's rays. Now, of course, what's going to happen in real life is that the sun is going to be moving, and that's why the angle changes, right? But this sort of just tells us the direction, so you can imagine it for the sun is somewhere over here. At noon, the sun is somewhere over here. So that's essentially what this component does, is it gives us the solar angles, so the altitude and azimuth of the sun. Does that make sense to everyone, kind of what we're doing? Great. So what we're going to do now is, you can imagine that shadows are caused because if we have a building here, and let's say we have a curb here, here's our road, our sun's here. So there's our sun. And essentially, if we don't want to shade this curve, what we need to do is we need to make sure that for a given time, our building doesn't intersect in a straight line between the building and the curb, right? So we know that this building is going to cast a shadow on this curve because at a certain time, the sun's ray extends like this in a straight line and the building gets in the way of the sun's ray, aka it'll cast a shadow. Whereas a building that's lower or at an angle, at this same time, the building doesn't get in the way, so the shadow is actually just going to cast down here, so this curve is still in sunlight. And essentially that's what we're going to do here. We're going to sort of just make sure that this solar ray never extends past the edge of this curve, and therefore essentially we'll define the envelope that way. So to put it a little bit more cleanly, what we're going to do is we have our curve here. Here's our potential building face. We're going to draw a solar ray from the base of our curve based on these solar angles, and we'll know that a building that stays underneath this group of solar rays will never cast a shadow on this sun, right? Because if it was higher than that angle, then it would, but because it is lower, it'll never cast a shadow on that curve. So what we need to do then is we need to select our curve. So like I said, this is something that you can sort of choose what you want to do, whatever, you know, essentially seems the most fun to you, which gives you the most interesting shape. So maybe let's try out two different shapes to see what I mean when I say that. So for example, let's look at this curve here. So this site, I'm just gonna, if you can't select a site, it's because it's probably locked. So just unlock your assignment sites. And what I'm gonna do is I'm just gonna select this curve. Oh, sorry, it's the context that's locked if we're selecting sidewalks. So I'm going to select this sidewalk here. This is the sidewalk I'm going to try first. And then what I'm going to do in Rhino, I'm just going to go to curve. So curve from objects, duplicate edge. And I'm just going to duplicate all the edges that I might want from this sidewalk. So like that. So if I'm choosing this sidewalk right here that I don't want to shade this sidewalk, I'm going to choose these curves, right? Now, that is the curve I don't want to shade. I'll click join just to make sure it's in one curve. So this could be potentially the thing that defines my envelope. So let's choose this one for now. So what I'm going to do, I have this curved line I need to reference in Grasshopper. So what I'm going to do is in Grasshopper, I'm going to go to Params, Geometry, then Curve. I'll drop it on the canvas. I'll right click on curve, go set one curve. So I've selected this curve that's north of my site. So again, it just needs to be north of the site. And then what I'm going to do is I'm going to go to surface, I'm going to go to freeform, and then I'm going to go to extrude. I'm going to plug my curve into the base. In the direction, it's going to be my vectors coming out of the amplitude. So my solar vector goes into the amplitude's going to go into the direction. And you can see what happens is I have these extrusions coming out the bottom of my curve. And that makes sense because the sun points down, right? But what we want to do is right now what we're showing is we have our curve there. We have our lot, you know, this is our lot right here. The sun is up here. The rays are going down like that. That's what we're seeing right there. We want to reverse these rays to bring them back up towards the sun. And that's what allows us to derive our solar envelope, right? So what we can simply do is our amplitude right now, we set it to be at 100 strictly for visualization purposes up here. What we can do instead is we can right click that amplitude, go set number, and switch it to, let's say, negative 500, and then go commit changes. Essentially what you want to do here is you just want to make sure that it extends over your site, right? So if we're defining the height envelope derived from the solar shading, we just want to make sure that we're covering our site. So for example, if you have a solar envelope that looks maybe like this, where it doesn't cover your whole site, that doesn't count, right? You want to cover the entire site. So there we go. So that essentially are our solar envelopes for this day. So if we think about what this means, essentially what we're saying is that we have all these different envelopes that sort of come in, and if we can't shade the curve between the hours of, I'm just going to delete this vector display here, just because that was getting in the way, all those arrows there. So if this is essentially the shadows potentially cast onto this curve at, let's say, 4 p.m., you can see that essentially 4 p.m. it's going to be the solar angle, which sort of determines the height of the building because it's the lowest one here, right? So what we can do then is we can essentially just bake these. So what I'm going to do is I'm going to go new layer, and then I am currently analyzing March, so March 20th. So what I'm going to do is I'll just make a new layer called March 20th, and then I'll just call these solar planes. And then I will bake these extrusions. So I have my extrusions. I'll right click, I'll go bake, and I'll bake them on the March 20th solar planes. And then maybe group yes, please. So these are the March solar planes. So our building can't go higher than this. However, if you look at it in the site, maybe it can go higher at this level, right? So that's where the intricacy starts to come in. Now, remember, we also need to consider, so this is March 20th, we also have to consider September 22nd. So what we're going to do is we are going to lock our solver because we don't want to have a million extrusions. So make sure before you're changing the date here, you can either right click this Python component and go disable. So you can either disable that, or you can just right click on your canvas and go lock solver. Oh, sorry. And what we can do is we can essentially change our date with the solver locked. So now that the solver is locked, we can just go back to September. So we can slide over to September right there. We can slide to September there. So the fall equinox is September 22nd. So let's choose September 22nd. So just make sure that the days are the same. Tuesday, September 22nd, 2020. Tuesday, September 22nd, 2020. I can right click on my canvas again, go lock solver. And if we look at our perspective, we can see that the September planes are actually non-ruling, so they won't have much of an effect. That being said, they might for yours. So what we can do is we can make a new layer. So I'll go new layer, and I'll go September 22nd solar planes. And I will bake the September 22nd solar planes onto onto that layer. So I'll right click my extrude, I'll go bake, and I'll go September 22nd solar planes, group yes please. So now we have all these kind of layers. Now, since we only have 7 minutes left, we won't finish this topic today, but you know, it gives you sort of a start. But maybe since I don't have a ton of time, what I will do is I'll address what I meant when I say choose a solar plane or a curve that gives you something that's, you know, a more exciting or, you know, a fun envelope to deal with. And what I mean by that is, you can imagine if I have a surface underneath here, and I go, so I have my curve here, and then I'm going to go solid, extrude planar curve straight to the height of 250 meters. So roughly I'll say, you know, extrude 250 meters, and this moves up. You can imagine more or less that what's going to happen is that this area here will extend to the 550 or to the 250 meter mark, and we'll also get an interesting thing here, but you know, our overall form might not be the most interesting. So maybe I'll just open Grasshopper and refer to my notes to sort of illustrate this. So this is what we're working towards. So as you can see, I can't really get to the same point. So okay. So essentially what this is going to give us, so this is a preview of what we're going to do. Essentially we're going to make a definition that makes sure that our envelope doesn't go above these solar planes, right? So this thing here, and then there's planes here, I just didn't bake them. Maybe this is interesting. So if you kind of imagine like, oh, okay, this is a pretty cool building, it meets the requirements, this is the one I want to stick with. What might be productive is to explore other curves. So maybe this building isn't you know, the most interesting thing in the world. So instead of using these solar planes from this curve, what you could do is sort of, when I was investigating this, I actually found that the solar planes from this curve were the most interesting. So I could go curve from objects, duplicate face border, for instance, and now I have this curve here, turn on Grasshopper, and set my solar planes to be this curve instead. And the reason why I thought this curve was more interesting is because you start to see how the different angles give you these weird notches. Now in reality, I know that technically if you analyzed every single minute, that would fill in. But I mean, for the sake of this class, I think that having this weird kind of notch there might be kind of more fun than having a simple plane. So I just want to show you what I mean by choosing one curve to the north. So, I mean, since we don't have enough time to kind of start jumping into the next part there, I think this is a logical place to leave it, where we're just creating the solar planes. We've sort of looked at the site coverage. But does anyone have any questions about this topic, about where we're headed, or about assignment 1? Okay, so if there's no questions in general, what I'll do is I'll just stick around for a few minutes, and I know that I've answered most of the emails that have come through to me regarding assignment 1, but if there are emails I haven't gone to yet, there might be a couple, or if there are questions that you haven't emailed me that you want to ask me about assignment 1 in particular, I'll stick around for a few minutes for that. So regardless, all the assignment 1s I've seen so far are looking great, so thank you so much for your hard work, and essentially I look forward to working on to the next assignment, and I'll see you all on Monday. Thank you very much. Have a good night and a good weekend.